Okay, last class we were discussing about lasers and we discussed about types of lasers also. And we start that one of the examples, helium neon laser. Okay, and we discussed about the types of lasers also. Okay, and we gave, I think we had started approximately at this point. Okay, and here basically helium neon laser, as we know that they are at ordinary temperatures, they are gases. Therefore, we take this gas mixture in the ratio 1 part of helium and 0.1 part of neon. Okay, or we can also have the 10:1 ratio. The pressure, in terms of pressure, they have given. Okay, gas is measured in terms of pressure. Okay, and once we take that kind of a gaseous mixture as a medium, okay, we keep that entire our active medium in a glass envelope. Okay. And we have fabricated the gas envelope in such a way that we have introduced two electrodes. One is cathode and the other one is anode. Okay. And two ends of this entire glass envelope is fitted with two mirrors. Okay. This is here. This is output coupler and this is eye reflector. It is very much similar to, you can assume, or not only assuming it, the reality is that we keep 100% reflecting mirror here and we keep about 99% or 95% reflector the other way. And then that is the experimental setup. Usually for this particular chapter, we will ask you to explain the construction of helium neon laser and explain the mechanism with energy level diagram. This is the standard question. Okay. Now, I think we discussed about the construction. Let us see. And we also considered what is there inside in the ratio of 1:0.1. Okay, and the actual lasing is happening among the energy levels of neon. Though concentration of helium is more, the realistic, whatever we call it as so-called lasing medium or realistic transitions, what we are expecting, that is coming out of neon. And why are we using helium is the obvious question. Okay, because I need to create population difference. Okay, I need to create population difference among selective energy levels. Okay, for that purpose, exactly to cause a transition among selective energy levels of neon. Okay, I need to use helium. Okay, that is the purpose of using helium gases along with neon gases. Now let us look at the energy level diagram. I think last week all of you would have written this energy level diagram. Okay. Let us try to understand one by one. What we do is we have kept electrodes here, right? Cathode and anode. Between this cathode and anode, we supply very high voltage. Okay. We supply very high voltage, and this voltage discharges helium atoms. Okay, and they excite. Okay, the discharge of the gas make these helium atoms to go to higher energy levels, and these are the energy levels possessed by the helium atom. Okay, and these energy levels you can see. And these helium atoms go to 2s3 1 as well as 2s10. Okay, it is 2s10. Okay, 2s31. Okay. As I was mentioning that these are just places. Function places. So we have to select it what is really relevant to you. It so happens that we probably not even consider this one. All these places we have it here. The argon laser, carbon dioxide laser, all these things are extremely another notation what we use in order to this is 2 1s and 2 3s are the energy levels among helium atoms. Okay, and here whatever the energy level diagram we have written here. Okay, this is the selective energy levels what I have written for the helium. In the same fashion, if I consider neon, okay, there are plenty of energy levels associated with this. Okay, among them, it so happens are we have chosen the combination of these two gases in such a way that certain energy levels of helium are exactly at the same height as that of the neon atoms. Okay, by arbitrary or for some other reasons. Okay, therefore, what happens at this point whenever the excitation of electrons happen because of the discharge? Okay, and then these helium atoms go to higher energy level, that is 2 1s, 2 3s. Okay, this notation, exact bottom, superscript, subscript, let us not really do it. Like, just write it. Okay, and this represents state. Okay, what is the orbital quantum number? What is the multiplicity? What is the total quantum number you have studied about J, L, S, in the board of it? Based on that, these numbers are given. Okay, let us not really get into that. Let us try to understand later. Okay, these are the energy levels what we are carrying. Now, I am making basically the process by which I am making these helium atoms to go to higher energy level is called pumping. This electric discharge pumping has been adopted here to make the transitions among helium energy levels from lower level to higher energy level. And we have chosen the combination of helium gases and neon gases in such a way that especially these two energy states of helium are exactly at the same height as that of the 2s state and 3s states of the neon atoms also. Their energy levels are almost same. It is not only almost, but almost I can say that nearly 99.9% same. Okay, that is like people are in the ground state. Okay, I want to make some transition to occur in 407. Okay, but I take 406 as well as 407. I keep people from lower end to 406. And then you guys, whoever is making noise in the ground floor, will make them to jump to 406. And then you disturb them equally. And they just get disturbed and they come up. Okay, that's what exactly happens. Okay, this is making this helium atoms to go to hydrogen system because our, what I can say, same analysis. Now helium atoms are in the higher level state, but content of helium is much higher than that of the neon, 10:1. Therefore, more helium atoms are there in this room, which are already in the higher energy state. Then whenever they roam around, there are gas molecules. Whenever they roam around, they collide with neon atoms. And then they absorb this energy. Okay. They absorb this energy. Then these neon atoms, which are in the ground floor, they also get excited to exactly to the same. Okay. Therefore, by collision, okay, they transfer this energy to neon atoms and then go and excite and they see exactly at this point. Now I have transferred the population inversion mechanism from helium atoms to neon atoms. Now, because of the helium neon collision, okay, I have got more number of atoms in these states compared to that of the humans. Okay, this you can ask me a direct question is that why do you really need these people? Why can't you come to 407 and blast them and make them to keep? Okay, there are certain particular things. Okay, that is not possible among Myanmar. Okay, I cannot cause this population inversion among Myanmar. That's why I am taking help of the Indian atoms. I make these atoms to go to higher energy state, and then more number of people are. It's not going to make it. See, there are some selection rules associated with this. Okay, this selection rules and also the intermediate states. Okay, there are transition probabilities among these energy levels. Okay, it is little simplest answer what I can give is that if I just Google it about the transition probabilities and selection rules among the energy levels, I cannot cause transition among any energy levels. Okay, that is, really have to tell you that delta N should be plus or minus 1, delta S can be 0, plus or minus 1, delta J should be plus or minus 1. There are transitions and delta ML, MS, what we write, there is a separate S to S transition is not possible. Only the SPDF right? Okay, S to P, that means that S is 0, L is equal to 0 for S, L is equal to 1 for P. Delta N should be either plus or minus 1. Either it will go from S to P or P to S. It cannot transit from P to P or S to S or D to D. Again, D to S is not possible. That becomes plus or minus 2. That is what, like that, there are certain forbidden factors. Okay, that's why we are.
Sir?
Yes.
So why do we use helium and neon as compared to other gases?
I could not hear your voice.
So why do we use helium and neon as compared to other gases?
Reduce the speed of it. It makes a lot of difference. Switch off other places and close this door. Can you repeat it now?
Yes, sir. So can you hear me?
Yes.
Yeah. So why do we use helium and neon gases as compared to other gases?
See, these are all one is sort of inert gases, and also the energy levels among these two levels do match properly. We need to create population difference among these two, but carbon dioxide laser also is there. Okay, you can ask me. There are plenty of answers I can give you, but you should ask me why only this combination. That I can explain it better. Okay, carbon
Yes,
other
why that
gases.
combination?
This combination, as you can see, for helium atoms, the energy levels 2s3 and two 1s and two 3s states are having equivalent energy levels among the neon energy levels also. For neon atoms also, there are certain energy levels. They are at the same height compared to that of helium. That's why we have taken the combination of helium and neon.
Sir, but during helium and neon collision, is not energy is lost, no, sir, during the collision?
Energy is that. That's why neon atoms absorb that energy and go to higher energy.
The entire energy from helium atoms absorbed, sir?
Yes.
Okay.
Otherwise, if they take part of the energy, the population inversion would have occurred among other energy levels also.
Okay, sir.
And also, these energy levels, whatever we have considered, 3s and 2s states, they are the metastable states of the neon atoms. Okay, because remember, because it sees that our laser system should have proper energy levels and also those energy levels should be metastable states. At least atom should stay in those energy levels for a while. Okay, at least in the order of milliseconds or worst case microseconds, not in nanoseconds. Okay, therefore, these atoms also move here in the sense, usually these atoms move here is somewhere in the nodes or somewhere they explain, not that, not helium atoms will go on the activity space. It make these neon atoms to go to their respective energies. Okay, and then now I have more atoms. By default, we know that our original condition would have been how much? I will be having about 10 atoms according to Maxwell-Boltzmann equation. If there are 10 atoms here, here I will be having 8 atoms. Here I will be having 6 atoms. Here I will be having 4 atoms. Here I will be having 2 atoms. Here I will be having 1 atom. That's how exponentially population decreases when you go to higher energy level, right? Guys, are you able to understand this concept?
Yes, sir.
It went down, right?
Yes, sir.
When you go to higher energy state, your population is very less. This is the population. Okay, population is highest for E1, okay, and the lowest for E5 also. Like that, this is by default. Now what I have done, though it is under thermal equilibrium, at that point I am disturbing the thermal equilibrium here. Okay, because of the collision, these helium atoms make these neon atoms to go here. Immediately I have more population here compared to that of these atoms. Because I am doing a selective population inversion. Okay, and then once more atoms are here and more atoms are here, then let us think about the transition. Okay, and at that point, what happened? At this point, whenever this another collision comes into picture, okay, that energy is liberated. Okay, assume that first time they make this transition neon atoms to go to higher energy level, and then whenever these helium these atoms are coming, okay, and they are hitting these atoms, making this stimulated emission to occur among these energies. Okay, population inversion is occurred, and this entire description is given in the next slide. Okay, or I might have trying to give one bigger picture. Okay. What I can do is let me zoom it more so that you guys also can see. Okay. Now this is the entire picture. Now helium atoms went up, and now I have more. Oh, here is, I cannot use pen now. Okay. Here I have okay. I have more atoms here. I have more atoms here compared to the these ones. And here, okay, I can expect because always population in the more number of atoms here compared to that of here, and more number of atoms in this 3s state compared to this 2p state, more number of atoms are there in 3s state compared to 2p state. Okay, but as I was mentioning earlier, the transition delta S will be plus or minus 1, S state to P state, S state to P state here. Okay, therefore, transition is possible. Delta N is plus or minus 1. Don't worry about it as far as your syllabus is concerned. But all these transitions are possible. Okay, now we are getting, obviously there are three things. One is the transitions are possible among these energy levels. Second one is which one is dominating. Okay, when all these transitions are happening simultaneously. Okay, which one is dominating? Why is it so? Now remember here, from here to here, energy difference is very small. Okay, therefore the wavelength is very high, 3.39 micrometer. But here the energy difference is high, therefore wavelength is less, 632.8 nanometer. And here also I have one more transition. Okay, and this energy difference is small, therefore this value is also relatively high. The wavelength is high. These two are inversely proportional. And now you can imagine that if you compare at this point, usually we have 6, we have 4, we have 2 atom building blocks. I have created population inversion among only these. Then the population difference from here to here is very high, very important. Okay, and then this transition predominates over other two transitions. Okay, this transition is also possible, this transition is also possible, this transition is also possible. But among these three transitions, okay, this transition predominates. Okay, and there are, I will talk about that little later. Okay, this why does it really predominate over other transitions? Okay, one is obviously the energy difference is high over here, and I am getting more number of atoms here, therefore more intense light, more electrons can transfer, and then more photons can be coming out. Therefore, more photons means more number of photons. More number of photons are possible. And at that point, we also use some other mechanism to make these transitions less detected compared to the transition which is of interest to us. Okay, that will let us try to look at the next, right? Okay, and then we will come back and we will try to explain these concepts. First, let us try to see, and so that we can take notes further up to that point. Okay, now what we are doing, pressure of helium is nearly 10 times that of neon, as we discussed. Okay, it is 10:1. Okay, and electrodes are connected to high voltage source, few kilovolts DC. Okay, and mirrors are placed outside the tube with end windows of the tube placed at Brewster angle. Okay, that concept is, I forgot to bring the pen. Okay, if you look at some of these papers, what we do, okay, we keep mirrors at these points. Okay, this is the assembly, whatever we consider here. Okay, we keep mirrors at Brewster's angle. These mirrors are kept at Brewster's angle. Then we get the polarized light I can expect out of this. Okay, and the mirrors are kept at Brewster's angle. Ray of light incident at Brewster's angle. The reflected light is polarized perpendicular to the plane of the reflection. That would help us to cast some other mechanism here. Okay, only component oscillating parallel to the plane of the incidence will sustain lasing emission, and light emerging from the laser is linearly polarized. Okay, that is how the mirrors play an important role. Along with the regular 100% reflection, there is a default one. Okay, and then now we have understood that concept. Let us go back what really happens after that. Okay. Okay. Now what has happened? Atoms, these whatever the transitions which are happening, okay, what I am doing is I am adjusting the dimension of the room in such a way that, as I mentioned earlier, only selective wavelengths can sustain within the room. Okay. So that what I can do is the amplification what is supposed to happen within the cavity, I depress the amplification to be happened for these transitions 3.39 micrometer and 1.15 micrometer wavelength lights to be suppressed so that my lambda length of the cavity is integral multiple of 632.8 nanometer. Then only those wavelength photons sustain within the room, and then only they will come, one of this 638 nanometer photon will go and get reflected back and it will come and hit this. Then obviously stimulated emission to occur means energy level should match. Then only transition would happen from here to here. Then two photons will be emitted. Then those two photons again hit the mirror and come back and hit this neon atoms. Again four, instead of two photons, now four photons. Like that, millions of photons will get accumulated simultaneously. And then what happens whenever these atoms come here, now there is no mechanism for these atoms to go back there. Okay, that's why what happens from this one, okay, there is fast radiative transitions. Okay, fast radiative transitions whenever we talk about is that this is a unstable state. 2p is an unstable state. As soon as electrons or atoms come to that level, they immediately dissipate. Okay? They immediately spontaneous emission occurs. That's what we call it as fast radiation. And then they come to lower energy level. And since they are all spontaneous emissions, there is no coherency among all these photons, but they are still radiative transitions. Okay. And sometimes we use, once they come to one state, that is not the ground state by default. Okay. And then they have to come back to its lowest energy level. Okay. How do they come back? Again, these neon atoms diffuse towards. These neon atoms, they come to lower energy level, they go on collide with the walls of the container, they losing their entire energy, and then come back to ground state. And whenever they come back to ground state, immediately these excited helium atoms make these atoms to go back to the highest state. This cycle completes. Okay, and it is a continuous process. It is not, that's why it is a continuous process, continuous. We get this lasing to happen among these transitions. In certain examples, we do talk about non-radiative transitions. That means the transitions are occurring, they do not give out photon. Okay, that energy will be converted for some other purpose. That could be here, one of them is diffusion with the walls of the container or molecular vibrations. Okay, that energy will be liberated for some other purpose, not for useful purpose. That in our spectroscopic terms we call it as non-radiative transitions. Okay. We are not violating the conservation of energy. Only thing is, whenever the transitions are occurring from one state to ground state, okay, I am not getting any radiation over. That energy is already absorbed by the given system itself to increase the heat of the molecules. Okay, the thermal energy of the entire system will get utilized. Okay, and our vibrations, rotations, and all other parameters we can consider are one of the best examples. At this level, we talk about diffusion of the walls. They can go and collide and they will be there. The way whenever the bond is moving faster speed, okay, it will go and hit that one point and it stops, right? That's it. Okay, understood this energy level diagram? Okay, this is very, very important. Okay, we have to explain this mechanism. What happens in the exams? Some people either write the explanation, they would have got the, they don't write the diagram. Okay, some people write the diagram, okay, they don't explain anything. Okay, both of them are memory based. Okay, you remember the picture or you remember the story. Okay, unless you have both of them, you cannot judge whether you have understood or not. Okay, both are important and also this transition. If you remember this picture and all these transitions also, okay, then you can always create the story. Okay, entire thing is important and construction of the helium plays in the way we design that also equally important. Okay, and if you know purpose of all these things, you can always hook up the story at that point. Okay. This all about the energy level diagram and working principle. Okay, and we get polarized light out of this. And the speciality of helium neon is we use mirrors which are kept at booster angle. We get the polarized light out of it. Then why this helium neon I am really concentrating telling about is that whenever you measure the intensity of the light coming out of the laser, and if I measure it as a function of wavelength, it might detect that. Okay, that light is coming out, what is the wavelength of light coming? If I have a detector which can detect all the radiations, then you can see that the spectral purity of this light is so high. Whatever the other transitions we did right? Small transitions, 330 nanometer or micrometer we wrote it, right? Those ones we don't see having it. So usually most of the other lasers, though this is the prominent light, there is a small light corresponding to here or there is a small another light. Because there are many energy levels. Okay, they are suppressed by adapting different methodologies. Like that, this is the spectral purity is very much highlighted. That's why this is used in many. Okay, we most of the research labs, okay, or even normal labs, we use this as a standard source for many applications within for other instances. For many other applications within the laboratory experiment, we use. That time we use it like a gadget. The way our point is a gadget. Like this helium has very good spectrum. Okay, we will discuss, continue from next class.